Right, let's try and do a quick summary of chemical bonding and intermolecular forces, and we're going to do this using a Venn diagram to try and help clarify our conceptual understanding. So the first key point is that both or all types of chemical bonding and intermolecular forces are all types of electrostatic attraction. So actually, if we're doing a Venn diagram here, then my three types of bonding and all the types of intermolecular forces can go inside this circle because they're all types of electrostatic attraction. So we've got ionic bonding, we've got covalent bonding, metallic bonding, and then my intermolecular forces. For more detail on each one, you might watch a separate video, but as a brief overview, ionic bonding is the attraction between oppositely charged ions. Covalent bonding is the attraction between a pair of nuclei and some shared electrons. In metallic bonding, the attractions between positive ions and delocalized electrons. And then for intermolecular forces, well, there's four types, so we'll look at the individual types in a moment. It's worth noting here that the three types of bonding are all considerably stronger forms of electrostatic attraction in comparison to any of the intermolecular forces, which are relatively weak. So let's take a bit of a closer look at the intermolecular forces then. Well, the first one you might have come across are London dispersion forces. The second type might be dipole-induced dipole forces. We then have dipole-dipole forces. And finally, we've got hydrogen bonding. And it's worth noting here that hydrogen bonding is actually not a particularly special type of intermolecular force. It's just a specific instance of dipole-dipole forces. So we'll come to the actual details in a moment. For that reason, I'm going to put the circle for hydrogen bonding inside the circle for dipole-dipole forces. As a quick overview of the types of attraction in each of these, London dispersion forces, which occur between all molecules, are the attractions between temporary dipoles and the temporary dipoles that the initial temporary dipole caused, or induced. For dipole-induced dipole interactions, we need a mixture of polar and non-polar molecules in my solution, and in this case the attraction is between a permanent dipole from a polar molecule and the temporary dipole formed in a non-polar molecule. Thirdly, we've got dipole-dipole forces which occur between polar molecules, meaning that these are attractions between permanent dipoles. And finally, as we said previously, hydrogen bonding is just a specific type of dipole-dipole force with a particularly polar bond, which requires a hydrogen that is directly bonded to an oxygen, a nitrogen, or a fluorine. And it's worth mentioning that if I have a selection of different substances and they all have a similar molar mass, meaning they'll have similar strength London dispersion forces, then comparatively the strength of these intermolecular forces increases from the left side of the Venn diagram to the right. And the last term that's worth mentioning, these types of intermolecular forces are known collectively as van der Waals forces. And that basically means any attractions between molecules that does not relate to actual bonds or any attraction to ions in a solution. And I think that will probably do it for chemical bonding and intermolecular forces. Hopefully this video is of some help.